Hello, this is Prof. Magnus, and what we're going to do is we're going to have a very brief review of the fundamental theorem of calculus for differential equation students. This would be totally inadequate for a first pass, and it would be totally inadequate for, say, a real analysis class. But this is just very much a quick and dirty. So let's get started on this. And here we go. Let's get rid of this for a sec. All right, here we go. What's a fundamental theorem of calculus? Now, so let's just do that. Well, what most students see as a fundamental theorem of calculus is what people know as the evaluation theorem. For example, let's say if you wanted to do the definite integral of a function between a and b, and let's say f is continuous on, let's say, ab, then a consequence of the fundamental theorem of calculus is that this is going to equal, first of all, an antiderivative exists, and that this will be equal to this, where f prime is equal to little f on the interval in question. Now, that's what most students see the fundamental theorem of calculus as. Now, strictly speaking, this is what's known as the evaluation theorem. And of course, in differential equations, you need to know this. But there's a bit more going on. And what the fundamental theorem of calculus actually deals with, and I'll just write it down. And let's say let f be continuous on some closed interval. You can actually relax that a little bit, but we're not going to worry about relaxation here. What it basically says that if you define the function, if we define big F of x to equal the definite integral starting at a, ending at x, and let's say we'll put a different dummy variable of integration, and let's say x is less than or equal to b, greater than or equal to a. So if we define this, notice this is now a function. Then we have f is differentiable, and the derivative of this function is actually equal to the function, the integrand, the function you're integrating on this interval. That's what the fundamental theorem of calculus says. And let's just take a look at an application of this. For example, let's say I want to define the SI function, sometimes it's called the psi function, to be the integral from 0 to x of sine of t over t dt. Now, if you're wondering, how can I define this integral when technically speaking, you can't divide by 0? You might recall that the limit as t goes to 0 of sine t over t is 1. So you might recall that. So that actually makes this integral work. I know technically it's an improper integral, but not really. So if you define this function, SI of x, what the fundamental theorem of calculus actually tells you is that the derivative of this with respect to x is going to be sine of x over x for x greater than or equal to 0, with the understanding of sine 0 over 0. We're going to define that to be 1. I know we should actually be doing a limit, but I don't really care about that right now. This is differential equations, but yeah, technically we mean limit as x over x as x goes to 0 from the right is equal to 1, but that's too much writing. So this is enough review to do the, this is enough review. You can now do the quiz problem. And the homework. But I am going to give you a little bit of an optional. And if you don't want the optional, you can stop watching now. But here's the optional. Question is why? Because this does look kind of strange, doesn't it? You're defining this function in a rather strange manner. And, you have this. Well, first of all, the reason why we might want to do such a thing is that, for example, in this SI of x function, this integral by itself cannot be done by elementary means. This is what's known as a non-elementary integral. It has an antiderivative, but the antiderivative is not in our usual collection of functions that we discuss in calculus. There is a technical definition of that will take us too far afield. We're not going to get into differential Galois theory. But yeah, this thing here, you can't integrate it by your standard calculus 2 techniques. You need special stuff, or you need to take a series or something else. Okay, so why should this function that we have here, why should it be differentiable, and why should the derivative be this? And this is sort of a quick and dirty. So let's go ahead and define f of x to be the integral from a to x of f of t dt. And let's remember what that means from calculus 1. Here's my graph of f. I'm drawing f as positive, but it doesn't have to be. This is x equal a, or t equals a, I should say. This is t equals x. And you know that this integral is going to give you this little area here. Now, if I add a little bit to this, you go to x plus delta x, f of t dt. And I should have actually used a different color here. Well, if you go to t equals x plus delta x, and assume delta x is so small that we stay between a and b, where we know f is continuous, we get this little extra bit right here, right? Now, and this is key here, from Riemann integration theory, that's where you did all the Riemann sums and that kind of thing. If you took the difference between these two, and again, this is from how you set up integrals, that's going to be the integral between x and x plus delta x of f of t dt. And it gives you this little green area here. So it gives us this green area right there. Right, so we do know that. Now, here's where the real hand waving really starts. This green area here, this green area here, notice it has a width and it has a height. This green area is equal to the base times a certain height. And the height, by something called the mean value theorem for integrals, it's going to equal f of x star for x star between x plus change in x and x. So we can find a height in between, such that if we have a rectangle of this base and this height, we get this little area here. I'm not going to prove that, but I think that's, at least it's intuitive enough, I think. So what we have is we have this f of x plus delta x minus f of x, and that's going to equal delta x times f of x star And both of these sides are equal to the green area that I showed up above. Both sides are equal to the same thing. So now you know what's coming. This looks like the start of a difference quotient. That looks like what you divide by. So let's divide by it. And that's equal to f of x star. Now that's a mean value theorem kind of argument, but where x star is somewhere in between. Now this looks a lot like the difference quotient, right? So in calculus 1, what you did to get a derivative out of a difference quotient is you took a limit. So let's take a limit as delta x goes to 0. And that's going to equal the limit as a change in x goes to 0 of this f of x star. Now this is where f being continuous really comes in. Remember, f is continuous and x star is somewhere here. X star is something between x and x plus delta x. Now, because f is continuous and x star is between x and x plus delta x, we know that f of x star limits to f of x as delta x goes to 0. Because remember, we're squeezing this interval here really, really tight. And this goes to this. And by continuity, we get the value of f. So what this shows two things. It shows that the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. It shows that this exists and it's equal to f of x as required. Therefore, by definition, we know that by definition that this thing here, we just showed that that limit exists. That's equal to f prime of x, which is also equal to little f of x, which is what we wanted to show. So in fact, what that does is that's sort of a hand-wavy proof that if we define f this way for a continuous function, its derivative is f. That is, big F is in fact an antiderivative for little f. And so now to actually do the problem, if you want to calculate this derivative, you just basically take this and plug in. Now, of course, you can do more. You can put another variable down here. You can make this a function of x, in which case you have to use a chain rule and all that, but you've had calculus 1. This is just a brief review of this so you can do the problems. So thanks for watching.